figured out prime numbers years ago. Okay, he's about to explain it.
In two different ways, and it would take hours to explain that. But the prime numbers fall on the notes F, B's, G's, and C sharps always. Those four notes out of the 12 possibility notes of notes. And then with the Fibonacci sequence, the Fibonacci numbers all are 11 of the 12 notes. They never ever land on F sharp, but they do on the other ones. So anyway, to do this, I take 13, for instance, and I divide 13 by 12, and this tells me I'm one octave. Where's 13? It's over here. Oh, excuse me. Yeah. Excuse me. The Fibonacci number 233, added all together, adds up to 8. So this would be 19 octaves and 5 notes above middle C. So if this is my piano, we run out, we have another piano, and another piano would be way out there. And it gets farther and farther, it just jumps bigger and bigger and bigger and bigger as the Fibonacci number, you got the Nautilus shell, for instance, gets bigger and bigger, so on and so forth. So anyway, put these things side by side. So I've got 0.08333, and I add the decimal here of 0.416666, so on and so forth. That's 0.5, and the next one's 0.5, the next one adds up to 1, the next one adds up to 0.5, 0.5, 1, 5, 1.5, 1, 1.5, 0.5, 0. Added all of those up together, 9. 9 is a super special number in this vortex.
Wow. The 369. That's just absolutely amazing.
So playing this out. I'm the first person to record this, by the way.
Oh wow! Well, do you mind if I put it online?
No, that's all right.
Oh, fantastic!
Got to get out there anyhow. So I'm going with the where the notes fall in the vortex, and so it's C sharp, C sharp, D, D sharp, F, and then G sharp, and then this C sharp, and then A, and it keeps on jumping larger and larger and larger, but it goes way, way out into infinity, so I'm just going to play this.
Infinitum.
Yeah, so it's... Oops, that's the wrong note. Where am I? We're going out to across the street from where Nick Tahoe's is and playing.
That's fantastic. All right, so you were saying?
Yeah, so starting here, so it's F, F, B flat, E flat, C sharp, E, F, Y, A, B, C sharp, C, and it follows this pattern out forever. Over, and we're going out. It repeats at the 120th, and I believe goes on forever, always following. So I showed you how the last digit repeats at 60, then to 120, and I believe that will keep on going out forever. And in that 120, the 24 repeats 5 times, and when you get to the 5th time, that's where the 120th is, and I believe, and I haven't figured it out beyond that because my computer will not handle the mathematics because those numbers get so big, but it has to. I believe it has to. Everything else didn't, and everything else I had done, always following this pattern.
Absolutely mind-blowing.
times, as it goes from 0 to 60 to 120, they meet up and then should repeat again out into infinity. Wow. So the other night, well, a few weeks ago, I'm playing this pattern, just ain't got nothing better to do. And I stopped, and next thing I know, I'm praying really intensely, and I kind of hear God saying, Andy, we haven't spoken in a long time. But earlier than that, I figured out where the prime numbers, because these arrows here come from what I did with the prime numbers, and then the Fibonacci numbers are here, and I'm playing out this pattern. And all of a sudden I realized that the notes O, which is B, and U, which is F, and W, which is my note G, and Q is C sharp, D flat. All of a sudden I realized that the prime numbers can only fall here on these 6 possible lines. And so after I was done praying, I went online and got the list of numbers which are prime numbers and Fibonacci numbers. And it was just a short list. There's, I think, 16 of these. And then the numbers that are primes and Fibonacci's, for the most part, land on C sharp, F, F, C sharp, C sharp, F, F, C sharp, F, G. Oh, as far as I can tell. And this drawing ain't too great. So in the vortex here, at 1, I'm finding C sharps, and at a digital root of 4, we're getting C sharps. At the digital root of 5, we're getting Fs, and at the digital root of 8, we're getting Fs. Amazing. Yeah, there's pattern. There's mathematical properties with the vortex here. Numbers, let's say, have flavors, and they come in 9 different flavors. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 is 1 plus 0 equals 1. 11, 1 plus 1 equals 2.
I never heard of it. That's great.
Yeah, and like I said, my absolutely brilliant friend Neil. I say he's just a young kid. He's 40. 62. Showed me how to do this. So here's the very last one. So on the charts out there on the cardboard, I'd only gone this far. Well, I actually went to 120, but this is the last one. The 83rd Fibonacci number is a prime number, also lands on the note F. And then I had to do these by hand because my well, anyway. So you take this number here, this last one, which is tens, thousands, millions, billions, trillions.
Wow.
Septillions, octave, whatever. Is 19164, so on and so forth and stuff. So at each one of the commas, I'm adding these numbers together. 1 plus 9 equals 10. 1 plus 3 plus 4 equals 8. 7 plus 0 is still 7. Plus 2 is 9. So I took each one of them, reduced them down to a single digit, and then took all of these, like 12, 1 plus 2 is 3, and 17, 1 plus 7 is 8. Reduced them down, and then it's 9, 13, 11, 17, and 17 again. Added those together, and we were getting down to these two add up to 50. That adds up to 8. And with 58, 5 plus 8 is 13. And with 13, 1 plus 3 is 4. In other words, this number, which I can't even fathom how big it is, or even know what to say after trillions, septillions, and stuff like that, whatever that number is. And you go around the digital roots, this number is going to be way, 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 way out there on this line.
Wow.
Which is also related into this triangle where these notes, C sharps, E's, G's, and B flats, always land on those there.
Wow.
I don't know if anybody knows this or not. And you're one of the very first people that I'm showing this to. So
This is amazing, Andy.
yeah, this is what I do in my spare time. I mean, you know, and I skipped math class. Well, I'll be honest with you. I skipped every other class too. And,
They are the most successful people around.
yeah. Here's the dials that are on the chord teacher.
Yes.
So here is the dials, and I want you to focus right here on these triangles and on these little stick figures. All of our 3-note chords form triangles. Our 4-note chords form trapezoids. We're playing music, we are really playing and listening to geometric shape. This is how I first started figuring this stuff out 23 years ago. So it's 10th grade, and I'm in math class, and our teacher's explaining to us how to measure outside angles of arc and inside angles of triangles. So I raised my hand. I said, hey, teach, any one of your students could actually use this math you're teaching us, like when we grow up, like when we get a job? He comes over and he sticks his finger in my face. He says, Willoughby, he says, shut up. He says, there's 1 or 2 kids in my class who are going to actually use this math when they grow up, but it's not going to be you. Well, why don't you shut up? So
Boy, was he wrong.
So the kids who can actually need this can actually learn it. Shut up.
Oh,
and
my God.
30 some odd years later that I started using that math. Unfortunately, I found out he had died. He had cancer, so I never did get back to telling that. Hey, I actually learned something.
Wow.
These are my...
I was going to say.
These are my 2 older grandchildren. I've also got another grandkid since the last time I talked.
Oh my God! Congratulations, Andy. That is wonderful. And is this up on the wall as I look with the camera instead of my eyes? Is that your son or daughter getting married?
Oh yeah, that's my oldest, my son and his wife, and they live out in Colorado.
Wow.
Parker, which is near.
Parker, yeah, of course, Denver.
Yeah, right near Denver. And my 2 grandkids are there, and then my older daughter's in San Diego. Her and her husband live 20 minutes from the beach and a few hours from. They can go skiing up in the mountains.
I was going to say you can head up the Big Bear and right there.
Right there, Big Bear.
Yeah.
And come down and then go swimming in the afternoon.
They can go skiing and snorkeling all on the same day.
And my youngest one,
if the traffic's good.
my youngest one, who pointed out the very first set of math, she just got married a year and a half ago, and they just had a baby.
Congratulations, Andy. What a success you are, sir. I'm very impressed.
Well, I'm hoping. And so my piano teacher, this is him right here. His name was Phil Giles.
Hey, Phil.
Yeah. He ended up getting cancer. He died also.
Oh,
But
man.
he pushed me really hard, and then I had this dream, and then started figuring this out.
I know.
So I'm showing him all of this, and
So I got to see in your van.
how it's all navigation and a clockwork. You start from the very bottom of the piano, running your finger from the very bottom to the top. This being the mathematical relationship of all of the notes, all the chords, all the keys, the steps, and very mysterious half steps of music. Came to me in an extremely, very, very, very vivid dream. Took 6.5 years to figure out.
Wow.
Came to me in a 5-minute dream.
Wow.
My goal is to single-handedly rewrite music for the entire world. And
It's going to happen.
for-
It's going to
for
happen.
math,
It's amazing.
which is what we hear. We hear math.
Yeah. It seems that everything is math
Mhm.
to a certain degree. I mean, you look
Yeah.
at fractals and everything.
I
It's
love that stuff. Yeah.
yeah, it's beautiful. Right when I was saying, when you were showing the Fibonacci numbers,
Fibonacci's,
as and they were going and they were transcending, just like when you look at like a great world religions, as above is below kind of thing. It just seemed to, it's
So-
one big rabbit hole.
This mathematical vortex here was
Yes.
discovered in 1974 by a teenager. His name is Marco Rodin. I believe he's from someplace in South America. I can't remember what country. But anyway, he's probably in his 50s, early 60s now. But discovers this vortex, and it does all kinds of crazy mathematical things here. And he's world famous from discovering this vortex.
Wow.
And all of the mathematical stuff. He travels the world teaching. And my friend Neil Strassner, who lives at Zig and Zag from here, he showed me the digital roots of numbers, and then the digital rays first, then digital roots, and then this vortex. And so many of the stuff that I did here all reduces down to nines, for instance.
That's amazing.
And yeah.
Wow.
Oh, so getting back to these triangles and these trapezoids that we're playing our music in, and all of our different chords form triangles and trapezoids. Now we watch guitarists, and guitarists play what they call a bar chord. And a bar chord is where they take their finger, put across all 6 strings, and then they got some shape, and they're strumming away, and they don't move their fingers, but they slide their hand up 5 frets, and then slide up 2 more, and then go down 2, and then all the way back down. And again, I'm not moving my fingers, I'm just moving my hand. A, D, E, D, A, D, E, D. So they're going A, D, E, D, A, D, E, D. Are literally taking one of these triangles, in this case here, scalene triangle, going from A, D, E, D, A, D, E, D, A. That forms a perfect scalene triangle.
And this is your chord teacher?
Yep.
I have to say it's remarkable.
And then the triangles, or the trapezoids that the chords make up, fit mathematically perfectly into the shape of our octave, which is really a heptagon. It's a 7-sided, 7-pointed structure. We call it 8, but it's really 7.
Phenomenal.
Out in the hall, let me show you
Okay.
something out there.
Oh, we're gonna see. Okay. Okay, so we're back. We're out in the. This is the original, right? This is the one I saw in your van when I first met you.
Yeah. I kind of carry. Well, actually, I have a smaller one, but this is the larger one. Excuse me. It's all angles. 0 degrees, 45 degrees, 90 degrees, 135, 180, 225, 270, 315, and at 360, it repeats. So we're going through angles. 0 degrees, 45, 90, 135, 180, 225, 270, 315. 45, 4 plus 5 equals 9. 90, 9 plus 0 equals 9. 135, 1 plus 3 is 4 plus 5 equals 9. 180, 1 plus 8 equals 9 plus 0 equals 9. 2 plus 2 is 4 plus 5 equals 9. 2 plus 7 equals plus 0 equals 9. And then the steps and the half steps, which are longer, but this one here is 202.5. 2 plus 0 is still 2, plus 4, plus 2 is 4, plus 0.5, the digits add up to 9. This one adds up to 9. This one adds up to 9. And some of them add up to 18, but with 18, 1 plus 8 equals 9, and so on and so forth. It's like looking at moon phases, but has nothing to do with our natural moon. But as our 0 degrees, 45, 90, 135, as it goes through what I call the short cycle. And if you look at the notes are, like if we're looking at where the moon is, it has nothing to do with our natural moon, but
Right.
the mathematics is extremely similar. It's like looking at moon phases.
Amazing. That's a good way to think about it.
Yeah.
It's a good a learning aid.
My piano teacher, who gave me the book Longitude, was about a clockmaker, and it's a long story. So they used to navigate ships around the ocean by using moon phases. They would also look at the North Star, and if you were lucky back 500 years ago, you had a compass also. You were real
I thought they just had the sextants to check the
Yeah,
the
so what they
degrees
would do-
from the North Star to
Right.
how far
So
away.
they would take the reading. Well, the North Star's up here, and
Yeah.
they would take the sextant from the horizon up to the sun and or up to the moon, and their perfect angles and stuff like that. But it wasn't accurate. If it was cloudy, for instance, you can't see the sun. And the stars above.
Right, or
And you're way
or it's
out in the
nighttime.
Or,
Exactly.
yeah, and if it's cloudy, you can't see the North Star, for instance. Or
I have to say that would have been terrifying to be at night and knowing the shore is only a little ways away, and running into it.
Well,
Gosh.
I'm glad you said that, because that's part of the whole story. So,
Hmm.
I think it's the year. 1592, I think it was. Anyway, England's at war with Spain. So they send 5 of the biggest, baddest battleships down to Spain. They have a naval battle, and they kicked Spain's ass. The 5 ships are sailing back. It's getting to be about sunset. The navigator takes the angle between the horizon up the sun, starts doing the math, and it's very complicated. It takes hours to do the math to figure out how far around the equator, and then how far from the equator up towards the North Pole to pinpoint where you are. Navigator makes a mistake. He's 60 minutes of time, which is about an hour, which is about 15 degrees. Thinks they're way out in the ocean. Sun sets. They're heading north towards England. They get to a place called the Scaly Islands, and the Scaly Islands are tiny little islands and a bunch of rocks that are either just below or just above the surface. 4 of the 5 ships hit the rocks. They start sinking. The last ship realizes what's going around, turn themselves around and way back out in the ocean, wait for the sun to come up. Now they can see land and stuff like that. They float back to England. And so the one ship gets back to England. So, well, we've got good news and the bad news. The good news is we kicked Spain's ass. The bad news is we lost 4 of our best battleships in the Scaly Islands. Out of the 4 ships that went down, there was about 2,000 sailors. They had about 500 sailors at each one of these very large ships. Out of the 2,000 that went down, 16 of them lived. So England offers this very large prize to anybody to figure out how to navigate ships around the ocean. And it was like about $3.2 million in today's currency to anybody to figure out how to navigate ships around the ocean. They didn't think anybody would be able to solve it, but they thought that everybody would send their ideas into London, and they would take everybody's ideas and give it to their wise men, and their wise men would be able to figure out a way to navigate without having to pay the prize money out. A clockmaker by the name of George Harrison, not George Harrison, John Harrison.
John Lennon.
No, John Harrison. He's a clockmaker, and he lives 50 miles from downtown London. Hears about the prize. He figures out all you really need to do to navigate, and let's pretend this is the Earth and the equator coming around here. We're in downtown London. You're out on the ocean and stuff here. This is a very exact angle, and it's also time. So it'd be like 4 hours worth of time, 120 degrees. And now you know exactly what time it is. If you know what time it is at home and know what time it is out on your ship, you can very precisely pinpoint where you are on the planet.
Here we go.
So he figures this out when he's 42. They didn't give him the money until he was 82. His son actually went and collected the money. But he became world famous and rich, but by the time they actually gave him the money, he was in his 80s and died a few years after.
Jeez.
But this is all a clockwork.
Unbelievable.
So as this goes... And so let's pretend this is the sun, this
1
is
minute.
the moon. So this is C, D, E, F, G, A, where is it? B, C, and then the hands eclipse, and it just goes around and around and around by each one of these angles. But it's like if you're in the middle, this is the sun, you're on the earth, you're looking out towards where the moon would be, and or it's also a note, it would be like looking at exact moon phases.
Amazing.
The only thing it has to do with the moon is I'm a lunatic.
I like it though. I like it.